Hey there, language lovers and AI aficionados, ready to decode the magic behind how machines process language.
Mm-hmm.
Today, we're taking a deep dive into the world of tokenizers,
Yes.
those behind-the-scenes heroes that help AI make sense of our messy, wonderful human language.
It's a fascinating journey, really. Imagine trying to teach your computer to appreciate a Shakespearean sonnet
Oh, wow.
or decipher a text message full of emojis. How do you even begin to bridge that gap?
Right. Our sources today unpack this very challenge, focusing on how tokenizers act as translators of sorts, turning our words and characters into a numerical language that AI can actually understand.
Yes,
It's like giving them the keys to a whole new world, wouldn't you say?
absolutely. And what's so intriguing is that it's not as simple as uploading a dictionary. AI models, for all their processing power, they don't inherently grasp the meaning behind words. They thrive on patterns and numbers.
So how do we get from to be or not to be to something an AI can actually work with? That's where tokenization comes in, right?
Exactly. Think of it like this. Imagine feeding a sentence like, Jim Henson was a puppeteer, directly into an AI. It wouldn't know where one word ends and another begins, let alone grasp the meaning of the sentence as a whole.
It'd be like staring at a bowl of alphabet soup and expecting to understand a Shakespearean play.
Precisely. Tokenization brings order to that chaos, breaking down text into smaller units that AI models can then process. Our sources dive into a few different methods, each with its own quirks and advantages.
Okay, let's unpack those methods. Where do we even begin?
Well, perhaps the most intuitive starting point is word-based tokenization.
Okay.
As the name suggests, it's all about splitting text into individual words.
So if we took our example sentence, Jim Henson was a puppeteer, we'd end up with a neat list of those individual words. Kind of like using the split function in Python, which our source points out as a basic example.
Exactly. It's a straightforward approach, but it has its limitations. For one, languages have massive vocabularies. Storing every single word, including variations like dog versus dogs, would require a ridiculous amount of computing power. And that's before we even get to all the different languages out there.
And then there are those less common words, the ones that make language interesting. Would a word-based tokenizer know what to do with puppetry, even if it recognizes puppeteer?
That's a great point. And that's where those infamous unknown tokens come in, often represented as UNK placeholders for when the tokenizer gets stumped. Imagine reading a book where every 10th word is replaced with UNK. You'd lose the plot pretty quickly.
Talk about a recipe for miscommunication. Seems like relying solely on words has its drawbacks. So what's the alternative? Our sources present character-based tokenization as another approach. And this one sounds intriguing.
Instead of words, we're going down to the letter, literally. Each individual character, space, and even punctuation mark becomes a token. Think about the phrase, let's do tokenization. Each of those individual pieces would be its own distinct unit.
That seems like it would solve the problem of those pesky unknown words. No more UNK cluttering up our AI's understanding.
To a certain extent, yes. And as one of our sources points out, this method can be particularly useful for languages like Chinese, where individual characters carry a lot more meaning than a single letter in English.
So it's like each character packs a bigger punch in those languages.
Exactly. But as you might imagine, there's a trade-off. While this method might seem simpler, it can actually create more work for the AI in the long run.
Oh, how so?
Well, breaking everything down to the letter can lead to incredibly long sequences of tokens. Remember, AI thrives on finding patterns, and those patterns are a lot harder to spot when you're dealing with hundreds of individual letters instead of a handful of meaningful words.
It's like trying to piece together a jigsaw puzzle with thousands of tiny pieces.
Mm-hmm.
It's doable, but might take a while. So we've got word-based tokenization, which is intuitive, but can lead to vocabulary overload, and character-based, which avoids unknowns, but creates these massive sequences. It's like choosing between a giant dictionary and a never-ending alphabet. What's the AI equivalent of a happy medium?
That's where our third contender comes in subword tokenization. This approach tries to strike a balance between the granularity of characters and the efficiency of words. It's like the Goldilocks of tokenization, finding that just right solution.
Okay, I'm all for just right. How does it work?
It's pretty clever, actually. Subword tokenization keeps common words intact as single tokens, but when it encounters less frequent or more complex words, it breaks them down into smaller, meaningful subunits.
So instead of getting tripped up by annoyingly, it would see it as annoying and gemily. two pieces that are probably more recognizable on their own and preserve the original meaning. It's like that old adage, divide and conquer.
Precisely. And this approach is especially well suited for languages with complex morphologies, where words are formed by stringing together multiple units of meaning.
Our sources specifically mentioned agglutinative languages like Turkish as a prime example. I remember learning about those in college. You can end up with these incredibly long words made up of smaller, meaningful parts.
Exactly. Subword tokenization helps break those down into manageable chunks, making it easier for AI to process them without getting bogged down by length or losing critical information.
So it seems like subword tokenization offers a good balance. We get relatively compact vocabularies, fewer unknown tokens, and the AI can still grasp the nuances of meaning. But once we have these tokens, these digestible chunks of language, what happens next? Our sources mention encoding and decoding. Can you walk us through that?
Of course. Remember, AI is all about the numbers. Encoding is the process of taking those tokens, those units of meaning, and converting them into numerical representations that the AI model can actually work with. It's like assigning each token a unique numerical ID.
So it's a two-step process, really. First, tokenization breaks down the text, and then encoding turns those tokens into numerical data.
Exactly. Think of it like this. Imagine you're sending a coded message, and each word is replaced with a number. That's essentially what's happening here, just on a much larger and more complex scale. And of course, there needs to be a way to decipher the code on the other end.
Ah, that must be where decoding comes in.
Yeah,
Taking those numerical representations and turning them back into human-readable text.
precisely. It's the reverse process of encoding. And it's not just about swapping numbers back to their corresponding tokens. Decoding also involves putting those tokens back together in the right order so that the meaning of the original text is preserved.
So it's like putting the pieces of the puzzle back together, making sure they form a coherent picture in the end.
Exactly. One of our sources gives a clear example using the sentence, "Using a transformer network is simple." The decoding process not only converts the numerical IDs back to the tokens using a transformer and so on, but it also makes sure they are arranged in the correct grammatical order.
That makes sense. You wouldn't want your AI to spit out simple as network transformer using after all that work. But this all makes me wonder, is there ever a time when a simple word-based tokenizer is the right choice? Or are the subword options just always better?
That's a great question, and it highlights a crucial point. The best tokenization method often depends on the specific task at hand. While subword tokenization offers many advantages, there are situations where a word-based approach might be more efficient or even more accurate.
It's like choosing the right tool for the job. No one-size-fits-all solution in the world of AI, it seems. But tell me, what are some of the factors that might influence that choice?
Well, the nature of the language itself is a big one. Subword tokenization shines in languages with complex morphology, like we discussed with Turkish. But for languages with simpler word structures, like English, the benefits might be less pronounced.
So if you are working with a language that has a relatively small vocabulary and straightforward word formations, a word-based approach might be perfectly adequate.
Exactly. It could even be computationally more efficient, as you wouldn't need to break down words into smaller units. It really comes down to finding the right balance between accuracy, efficiency, and the specific demands of the task.
This is all incredibly insightful, but I have to admit, my mind's already racing ahead. We've covered how these different types of tokenizers work, their strengths and weaknesses, but our sources hint at something even more complex: pre-training. Could you shed some light on that?
Absolutely. You see, just like those large language models we hear so much about, tokenizers aren't just magically born with an understanding of language. They often undergo a process called pre-training, where they are fed massive amounts of text data.
Okay, so we've gone from basic word splitting to AI bootcamp with these pre-trained tokenizers. It's a lot to process. But I have a feeling we're about to go even deeper. What lies beyond these foundational tokenization methods?
You're right, we've just scratched the surface. Our sources mention a couple of other techniques, byte-level BPE and wordpiece, that have been making waves in the NLP world. These aren't just random variations. They address specific needs as AI models evolve.
Okay, so less like choosing between a hammer and a screwdriver, and more like needing specialized tools for increasingly intricate tasks.
Precisely. Take byte-level BPE, for example. It's used in models like GPT-2 and was designed to handle a wider array of text, especially when character-level encoding might be too fine-grained.
So instead of individual letters, it's working with bytes. It sounds like it could get pretty technical.
It does get into the nitty-gritty of how computers store information, but the key takeaway is that it allows for a good balance between vocabulary size and flexibility. Then there's word piece, which is used in models like BERT. Think of it as a subword approach, but with some clever optimization tricks up its sleeve.
Optimization tricks, you say. Does that mean it's better at handling those really long, complex words we talked about earlier?
In a way, yes. Word piece is designed to be very efficient, which is crucial when you're dealing with the massive data sets these models are trained on. It's like the difference between a leisurely stroll through the dictionary and a high-speed race to find the exact information you need.
Speed and efficiency definitely crucial when you're talking about the sheer volume of data these AI models are processing. But it all begs the question, where do we even go from here? Are there limits to what tokenizers can do, even with all these advancements?
That's a question researchers are grappling with right now. We've made incredible strides in teaching machines to process language, but there's still a fundamental gap between how AI understands text and the richness of human communication.
You're talking about things like sarcasm, humor, the emotional weight behind words, those subtle cues that even we as humans sometimes struggle to interpret.
Exactly. Our sources don't explicitly delve into this, but it's the elephant in the room. We can break down a sentence into its smallest units, assign them numerical values, and train our models on billions of words, but capturing those nuanced layers of meaning, the tone, the intent, the unspoken context, that's a whole other ballgame.
It's like the difference between reading a transcript of a conversation and actually being there in the room, hearing the inflections in someone's voice, seeing their facial expressions. So much can be lost in translation, even with the most sophisticated tokenizer.
Precisely. And that's not to say that AI will never grasp those subtleties, but it highlights the immense complexity of language and the ongoing challenge of replicating something that we as humans often take for granted.
It really makes you appreciate the power of the human brain, doesn't it? All those intricate processes happening behind the scenes every time we speak, write, or even just think in language.
Absolutely. And it makes the work being done in NLP all the more impressive. Even with these limitations, the progress that's been made in teaching machines to understand and generate human-like text is astounding.
It really is. And as with any powerful tool, it comes with the responsibility to use it wisely and ethically. But that's a conversation for another deep dive, perhaps. For now, listener, we leave you with this. As we marvel at how machines decode our words, let's not forget to appreciate the beautiful complexity of human language, those layers of meaning that make us who we are. Until next time.